All right, let's just jump right in with a really wild idea. We're all used to thinking about the universe as being full of, well, things. Particles, planets, stars, galaxies. But what if that entire picture is wrong? What if reality isn't made of things at all, but of connections? Now, to even begin to wrap our heads around that, we have to start with the single biggest mystery in all of science. It's this nagging problem. The two greatest theories we have about how the universe works, well, they completely contradict each other. And that means something is fundamentally wrong, or at least incomplete. And here's the problem in a nutshell. On one hand, you've got Einstein's general relativity. It's beautiful, elegant. It describes the huge stuff, planets, galaxies, as moving through a smooth, continuous fabric of space-time. But on the other hand, you have quantum mechanics. It describes the tiny stuff, atoms and particles, as a world of chaotic, jumpy, probabilistic weirdness. One is smooth, the other is chunky. How can reality possibly be both at the same time?
So this is where our story takes a really sharp turn. Instead of trying to force these two theories to fit together, a new idea asks a radical question. What if the problem is our most basic assumption of all, the very idea of space? Maybe the universe isn't some big empty stage that things happen on. Maybe the universe is just the web of connections itself.
This right here is the heart of it. The idea is that at the most fundamental level of reality, there's no such thing as distance or angles or shapes. There's no geometry. There's only topology, which is just a fancy way of saying there's a network of points, and what matters is who's connected to who. It's kind of like looking at your computer screen super close up. All you see is a grid of pixels, but when you back away, a picture emerges. Our solid, geometric universe could just be the big picture that emerges from an insanely dense network of connections. So, if reality is a network, how do you describe it? Well, it turns out you can do it with just one single master variable. It's called the coordination number, or Z, and it's super simple. Z is just the average number of connections that each point in the network has. And this one little number, well, it might just be the dial that controls the entire universe. And for our universe, the universe that we live in, that magic number appears to be 14.4. Now, this isn't some random guess. It's a specific value from the mathematics of these networks. It represents this perfect balance point, the exact level of connectivity a network needs to be stable enough to hold information, but flexible enough to let things change. And that change, well, that's what we call time. Our whole reality is balanced on this razor's edge. Okay, so we have this number, 14.4, but here's where it gets truly mind-bending. What happens if you just tweak that number? What if you change Z, the density of the network? You don't just get a slightly different universe. No, you get completely different states of reality. First up, what if Z is less than 14.4? Well, then the network is underconnected. It's floppy. It's loose. So a particle, which is just a little tangle of information in the network, can't really be pinned down. The web is so loose that the information just kind of spreads out into a wave of possibilities. All of a sudden, quantum uncertainty isn't so strange. It's just what happens when you're on a wobbly, sparse network. Now, when Z is right around that magic number, 14.4, you get what's called the critical network. And that's us. That's our universe. It's perfectly balanced. It's stiff enough to pass information along reliably. That's cause and effect. That's the speed of light. But it's just flexible enough to allow for change, for the flow of time. It is the absolute Goldilocks zone of connectivity. But what if you push it too far? What happens if you crank Z above 14.4? The network becomes overconnected, overconstrained. It's like pulling a knot so tight it completely seizes up. Nothing can move, nothing can change. Time itself literally stops. And this, according to the theory, is exactly what the inside of a black hole is. It's a frozen region of space-time. So this is amazing, right? One number gives us three totally different realities. But it goes even deeper. This idea suggests that the fundamental forces we've been trying so hard to unite, gravity and quantum mechanics, they aren't fundamental at all. They're what we call emergent properties. They just arise from the collective behavior of the network, kind of like how a traffic jam emerges from the actions of individual cars. Okay, let's just walk through the logic, because it's actually pretty straightforward. Step 1. The number of connections, Z, determines how stiff the network is. Step 2. That stiffness controls how much space-time bends when you put matter in it. Step 3. The way space-time bends, well, that is gravity. So gravity isn't some spooky force. It's just a direct consequence of the network's wiring.
And this totally reframes what a particle even is. It's not a tiny little marble, it's more like a snag, a little tangled up defect in the fabric of the network. When that tangle moves through our nice stable z equals 14.4 network, it behaves like a good little particle. That's classical physics. But if that same tangle wanders into a region where z is lower, the network is floppy, and the tangle just unravels into a cloud of probability. And that's quantum physics. Same particle, different neighborhood.
Now, I know what you might be thinking. This is a fascinating story, but is it just philosophy, or is it actual science? Well, the beauty of this model is that it's absolutely science. It's not just a nice idea. It makes very specific, very testable predictions about what we should find when we look out into the cosmos.
This is where the rubber meets the road. The theory predicts that way out in the huge, empty voids between galaxies, the network should be looser, z should be lower. And if that's true, then the fundamental constants of nature we learn about in school, they shouldn't be constant at all. In those voids, gravity should actually be a bit stronger, quantum effects should be bigger, and the force of electromagnetism should be weaker.
And here's the kicker. One of these predictions, the one about the strength of electromagnetism, it actually seems to match real data we already have. Astronomers have observed this strange thing called the alpha dipole. All it really means is that electromagnetism seems to be a tiny bit different depending on which direction we look in the sky. And guess what? That's exactly what this network theory says should be happening. It's a seriously tantalizing hint that this whole idea might be on the right track.
So let's just bring this all home. This framework is asking us to completely flip our view of reality on its head. To stop seeing the cosmos as a bunch of lonely objects separated by a whole lot of nothing, and instead see it as one single, unified, mind-bogglingly complex web of connections. And that really leaves us with this one last huge question. For the last 100 years, physics has been this epic hunt for the smallest possible thing. But maybe we've been looking in the wrong place. Maybe the deepest secrets of our universe aren't hidden in some new, undiscovered particle, but in the simple, elegant pattern of the connections that tie everything together.